My name is Brian Merton,
I'm Mohammed Dalali.
and our project was on affordable solar energy. I did most of the report side of the project. Mohammed was responsible for the design portion. And as far as the problem statements go, the first thing we wanted to do was define what affordable solar energy was. And you could really think of it in a lot of different ways. The first way you can think of it is, you go to your Home Depot or your Ace Hardware and you buy, a little solar panel and you stick it in your front yard, and that gives you enough light to, light up your walkway. That's not what we want to do. The second is on a corporate level, you want to reduce your costs, say, by 30% or something. So you line, the ceiling of your buildings with these solar panels and hope that, or not hope, but you project that it'll reduce your costs. We didn't really want to go that way either. What we decided to do is to revolutionize the game of solar energy, and not just solar energy. We wanted to revolutionize the game of energy. The sun puts out more energy than all other forms of energy on Earth combined. The sun actually puts out over 1,000 times more energy than the Earth consumes annually. So if we can harness this energy, there's no need for any other energy. All we need is the sun, and this radically changes everything. So how can we modern designs be improved? And to improve a design, you have to understand what the problems are. The first problem is inefficiency, and you can't really fix inefficiency. The way to fix inefficiency is you have to make it more efficient, and that's a lot easier said than done. And over the course of the last 250 years, where solar technology has really played a part, there has been a growth. And but still, you really are limited and you're handicapped by the technology that you have. So the inefficiency is not something that we really could play with. The second problem was quantity. And the thing with solar panels, if you have one little solar panel, it's going to collect X amount of power from the sun. If you have 30,000 of these on a pallet, you all of a sudden have 30,000 times more power. So what we wanted to exploit in this project was quantity, and we wanted to go in a huge scale. So we wanted to design a system which achieves affordable solar energy, and that is what we did later in this project. So we want to bring it back to the history of this whole thing. Solar energy really started in the 7th century, before the Common Era, and you had Romans and Greeks who were using magnifying lenses to start fires on torches, and they have written accounts of this. It wasn't really till the 1st to the 4th century about that Greeks and Romans started to use this technology to help people beyond just starting fires. You had these bathhouses, beautiful bathhouses, and what they would do is they would put windows facing the south, and the sun would heat these pools, and this is where they would congregate the whole city, and they would spend time, sort of like a pool washing area for them. It really wasn't until the 18th century that solar technology really took off. In 1767, a Swiss scientist was credited with creating the first solar collector, and that was really the beginning of modern solar energy. It wasn't until 1839 that the invention of the photovoltaic effect was discovered, and that was by a French scientist named Edmond Becquerel. And this really revolutionized the game, and it put the path of solar energy in a completely new direction. The photovoltaic effect, it's sometimes referred to as the PV cell. It's much easier to say. But what photovoltaic basically means is collecting sunlight and transmitting it directly to electricity. And it's really a marvel. The only problem with it is that it's incredibly inefficient. And in the early 1950s, it was the first that came out was 4% efficient. And then about 16 years later, they improved it to about 14% efficiency. Still, that's awful. Any mechanical system that has 14% efficiency is no good. It wasn't until 1992 that the University of Southern Florida finally broke that 15% barrier as far as efficiency for PV cells. At the end of the century in 1999, Spectralab Inc. developed the most efficient PV cell of all time. It was 32.3%. And since then, in 2014, I believe, the most efficient PV cell of all time is now at 43.5%. So that's sort of where we are now. It's still an inefficient system, but it's much more growing than it was. So now I'm going to give it to my friend Mohammed for the design portion of our project.
So I'm going to talk about the design. There's 4 types of solar panels in this world. There's like the monocrystalline silicon, which is a single layer silicon, and there's the polycrystalline silicon, which is a multi-single layer silicon. And we have the PIPV, which is the building integrated photovoltaics, and the hybrid solar cells. We in this project, we chose the monocrystalline silicon, and for many reasons which we're going to explain now. Of course, it has the highest effective efficiency because it has the highest quality of silicon, and it also uses the less space between all those panels, the 4 we just mentioned. So it has less space and more efficiency than any other panel. And it also lasts longer than any other panel. It's also like around 25 years and maybe more. And for the monocells, which you can spot from looking at just any panel, it has an octagonal cells, which has an unused space at the corners of each cell. And these cells are very high in performance in the low light than any other cells from also the 4 other panels. So now I'm going to talk about the specification of the design. It's going to be all frame, no screws, only 8 holes where you can install the panels easily with no efforts. The design is going to have a high transmittance, low iron tempered gas, and also the model is going to incorporate high performance bypass diodes, which minimizes the power drop caused by the shades. The conceptual design that we're thinking about is based on a project that NASA is working for 2050 to be implemented and ready to use, hopefully. It is a space elevator which has counterweight in the space, which is linked by a cable either by carbon nanotubes or diamond nanothread, which is the carbon is linked to the counterweight. And we can put panels on the counterweight to provide power to the elevator itself, and also so we can transmit the power back to Earth if we needed it. We can do it in 2 ways, either wirelessly through laser or through the carbon nanotubes, since they can transmit electricity. In conclusion, if you look at this project, it's going to be a long-term project, but it's going to have a lot of benefits, and it's going to stay for a long time. And for the environmental impact and sustainability, if you think about how it's going to save many things that we've been ruining to the environment, like chemicals or bad things that we do to the environment through like burning gas or oil or whatever. The risk assessment, it's about how you see it. It's either it's a big project. It's gonna have a big risk, but it's also gonna have lower risks in other places, like in the rocket fields. It's gonna save us without making any rockets feel any chemicals. So it's about how you look at it, and it depends on your perspective. And thank you.